So we've been talking about acids and bases. We've been talking about what they are chemically. We already know what they are from a nomenclature point of view, particularly acids, because they have their own kind of nomenclature. Bases, not so much. We want to get into calculations with these things. Now, because they're solutions, all of our solutions calculations will apply. We can talk dilutions, we can talk how much mass of this, or so on. So we can do all that stuff. But specifically, the pH. We know the pH is a measurement for how acidic something is or how basic something is, and we know there's a scale that goes with that. So we know that 7 is neutral, and we know that going to the left means more acidic, and going to the right means less acidic or more basic, depending on which way I'm going. And it is one of those backwards things in chemistry where the smaller the pH, the smaller the number for pH, the more acidic something is. But if you ever stop to wonder what that number actually means, well, let's give us a couple more things that we already know first, a couple more recall statements. We know that acids dissociate. We know that we could start out with the chemical formula of an acid, and let's just take one that we've had in nomenclature, and we could name that thing. And we could write that into its dissociation constant or process. Now we also know that the H plus reacts with water to make the hydronium. Now we can do that all in one step by saying my acid reacts with water to make hydronium and chloride. So there's a couple of ways we can think it through, whether it's breaking down into H plus or whether it's reacting with water to make H3O plus. Either way we end up with this thing, and that's a pretty important thing. Having said that, that thing, hydronium or hydrogen ion, in water anyhow, they're equivalent. So if I flip back and forth between talking about hydrogen ion or hydronium ion, they do mean the same thing. Okay, they are equivalent in water. Third thing that we kind of need to know is that bases are going to dissociate to produce hydroxide. However, for this video, we're really talking about acids. So the base thing we can tuck away in the back of our minds for a little bit. And then the fourth thing we know rather, is that strong acids and strong bases dissociate 100%. In this course, we're pretty much only going to be talking about strong acids and strong bases. So we don't really need to worry about the weak side of things other than they're there, just so that when we eventually do get to them, or when we do talk about them a little bit, we're at least familiar with the concept. And what that 100% dissociation means is that if I have a bottle that says 0.015 mole per liter HCl, that's a strong acid, so what I actually have is 0.15 mole per liter H3O plus. Okay. Now, a little aside, you'll notice that when I'm typing, a plus goes on this side. When I'm writing, it goes in the middle. Doesn't mean any different. Sorry, there's no difference between the two. It's just where is it convenient for me to put it when I'm typing, where is it convenient for me to put it when I'm writing. It's all about me. Okay, so let's start with an acid solution. Here is the calculation that we need to have. And what that means in English, or at least approaching English, is that pH has a number. pH is the negative logarithm, okay, negative logarithm of the hydronium ion concentration. Now that raises an interesting question, because what in the world is a logarithm? Take your calculator. Now I'm assuming that most of you have a graphing calculator. If you don't have a graphing calculator, your situation will be a little bit different. But if you find your graphing calculator, it will have a log button. And the log button is going to be there. Any scientific calculator will have a log button. Even if you pulled up the scientific calculator on a computer, the Windows calculator, there's going to be two versions of it. One is a scientific, one is a regular calculator. If you look at the scientific, it will have a log button. If you've been using your phone, you're not supposed to be, but if you have been using your phone, it might not have a log button. So you might finally have to get a calculator. Or remember to bring it. Okay. When you find that button, now we can go back and try out that button just to find out what the button is doing for us. And you would type it in pretty much the way you would type in a lot of things. So you'd press the log button on your calculator, type in the 1, and then the equal sign. Not that hard. And when you did that, and you do that for the log of 1, log of 10, and 100, 1000, and 50, you're going to get these answers. Now, if you haven't done this, please do this. It's always best to be pushing the buttons rather than just watching, right? Mathy type stuff is not a spectator sport. You get these answers. So the log of 1 is 0, the log of 10 is 1, 100 is 2, the log of 1000 is 3, and the log of 50 is that. Now, up until the last one, you might have thought, okay, the log button kind of tells us how many zeros there are. And it's related, but not quite that, because I can do a log of 50. If I were to take decimal numbers, decimal 1, decimal 0, 1, decimal 0, 0, 0, 1, and so on, and do those numbers, and again, pause it if you need to, and to actually do the button pushing, I get these numbers. Well, obviously, I'm not counting the number of zeros here, but in a sense, I'm counting the number of places the decimal point has shifted until I get to the last one. So what does it do? We could spend all day trying to figure this out. How about I just tell you? The log button calculates the exponent on 10 that would give the question. Now that doesn't really help you much, does it? Well, let's think about it this way. The log of 1 is 0, so ignore all the stuff below. The log of 1 is 0 because 10 to the exponent 0 is 1. The log of decimal 0,1 is negative 2 because 10 to the exponent negative 2 is 1, or sorry, decimal 0,1. Another way to think about that, you know negative exponents. How do you get rid of a negative exponent? Well, you put a 1 over that thing to the positive exponent, which would be 1 over 100, and the decimal equivalent of 100, or 1/100th, is decimal 0,1. On the other hand, 50 and 0.35, those were the two that were kind of strange numbers. But if you had 10 to the exponent 10 to the exponent 1.699, you'd get 50. Now, if you're trying this, you might be thinking, hey, you don't get 50, but rounded off it is. Okay, so you end up with a pretty long number here, which I rounded off to 1.699. So using that rounded off value, I get something pretty close to 50. And likewise, decimal 35 gives me negative 1.456, not planned at all. And 10 to that exponent is 0.035. Okay. Now, if I think about this, for solutions, I'm usually dealing with kind of smallish numbers, right? My concentration numbers are never going to be all that large. So, continuing on, going back to pH, if my pH is the negative log, so I know what the log button does, of the hydronium ion concentration, I said that earlier, and I have a concentration of 0.01 mole per liter, that would mean I would have a pH of 2. Alright, so let's try some. So what I have are some concentrations, some fairly small concentrations. And if you don't know how to do scientific notation on your calculator, again, I'm assuming a graphing calculator. There's a button called EE. And on the graphing calculator, there's actually a second function somewhere right above the top row of the numbers, like 7, 8, 9, those numbers. Right above there, there's going to be a second function. As soon as you do that on the calculator, it automatically takes into account times 10. So you would type in this, 1, second function, whatever the button is, might be above the comma, second function, negative 5, and it'll take care of that. If you want a better look at scientific notation, there's a video for that. If you go right back to the beginning of Unit 3, or if it's, I think it's also on the very front page of our course webpage. Anyhow, if you didn't need to do all that, and maybe you pause the video to calculate these things out, here are the answers that I got. Okay, so the pH of a solution that is 0.025 moles per liter, I get 1.6. If it's 10 times diluted, so decimal 0.025, you'll notice that these decimals are the same, but that number is different. And that's not just a coincidence, by the way. And if my concentration is a little bit higher, my pH is a little bit smaller. And if my concentration is quite a bit smaller, my pH is a little bit higher. Well, sometimes we know the pH. We can take a pH paper, we can get a pH meter. There's a lot of ways we can know the pH, and the question becomes, well, what does that mean? We know how to calculate pH from concentration. Can we get a concentration from the pH? Well, of course we can. Okay, so here's the calculation for pH. Sorry, if I know the pH, here's the calculation for knowing the concentration. So my concentration over here, concentration of hydronium ion, is 10 to the exponent pH, negative pH rather. So if pH is 1.5, then the concentration of hydronium would be 10 to the exponent negative 1.5. A couple ways of doing that. You can do a second function above the log button, but you can also use 10, and again I'm assuming graphing calculator, let me fix that, 10 little hat to the which means to the exponent of negative 1.5. If you do that, you'll get this number, or very, very close to it. So we're going to be rounding off a bit, right? How about the pH being 2.1? Well, do the same thing, 10 to the exponent negative 2.1, and I get a concentration of decimal 0.00794, or roughly decimal 8. But if you're looking at your calculator and mine says decimal 0.008 and yours says 0.079, all right, I don't want to mess you up. And if the pH is 3.8, again, pH is getting higher, my concentration should be getting smaller, and I end up with this. Now, please do this one for sure so that you can take a look at your calculator and see what your calculator does when the number is quite small. So what I used, put it into scientific notation for me. Yours might not. You might have decimal 0.000158 or something like that, or it might show it a little bit different. But this is how you would write scientific notation. For pH calculations, that's really all there is to it in terms of pH. Once we start moving into bases, things will have to change. But for moving back and forth from pH to concentration, from concentration to pH, that's it. Two things. And we're going to have to keep them straight. And the base ones will be similar enough that we can pick them up pretty quickly, different enough that we can get them confused. This will be awesome. No, not awesome. But we'll get there. So, talk to you later. See you in class. Take care.